RubyConf Taiwan. Yeah, it's my first time here, both the conference and the beautiful island of Formosa. I can totally understand Portuguese explorers that decided to call it a beautiful island. So my name is Andrei. I'm originally from Russia, but I have been living in Japan for 3 years now with my family. I'm a backend engineer, working primarily with Ruby and PostgreSQL and everything around. But you know, it's a lie. I need to confess that for real I'm an alien, a Martian. Don't worry, I come in peace. Okay. Jokes aside, I'm a backend engineer at Evil Martians, a software development agency for developer tools startups. As a consultancy, we help our clients to build their products, starting from product design, backend, front-end, deploying it to production, and ensuring that their products are working fast, reliable, and scalable. By the way, I asked Google Translate how to translate our company name. It said this. It looks good. It's very close to Japanese translation in terms of hieroglyphs. So please, Taiwanese people, confirm, is it a good translation? While we, Evil Martians, earn our bread through custom development and consulting for clients, you may probably know us by our open source, and actually probably your application will have a few gems that are authored by Martians in your gem file. And yes, we are using Kubernetes to deploy and run our applications from 8 or maybe 9 years already, starting from the very first stable release of Kubernetes. And while our DevOps department is small, robustness of Kubernetes allows us to deploy and run applications with minimal effort. Why Kubernetes? It gives us flexibility and control over the application architecture without tying us to a specific cloud provider. Kubernetes makes it easy to extract or add a component to application. If you feel that your all-in-one production image became too bloated and started to crash because of too many conflicting dependencies, that can happen, for example, if you use libvips for thumbnail previews creation and add some, add-ons to it. You can just throw it away, make your application code simpler, and instead introduce image proxy, which is also authored by Martians, as a microservice. And it will make things much simpler, and you will be able to scale it independently, and etc., etc. And if you need one more staging or even run a copy of your application for every pull request, it's also possible. So just create a new namespace in a Kubernetes cluster, execute Helm deploy, and it will be start running pretty soon. Of course, you can scale every component independently of your application, and last, but not least, you can run the same setup on different cloud providers. Every major cloud provider today has a managed Kubernetes service, so if you need, you can migrate between clouds, but for us as a consultancy, it means that even if a new client works on a separate cloud provider, we can, use the same, practices, the same Helm charts to deploy for them. All these benefits come with a price. Kubernetes is a complex system with a lot of moving parts and new abstractions that you need to know to be able to use it effectively. So why I, an application developer, the one who just develops features and fixes bugs, today going to talk about DevOps stuff? First, it's quite convenient when you may avoid waiting for your SRE colleagues to help you to deploy your application if you can do some of these changes by yourself. And even when DevOps gets free, they will still come to you and ask questions like, oh, how many CPU and RAM your component will need? Can you please also order special endpoint for metrics, special health checks, etc.? Like, you can do it by yourself. Again, it will save you time. So the better developers understand how their production environment works, the more reliable code, the more reliable application they can develop. That's why we at Evil Martians at one point even made an kind of internal Kubernetes school, like our SRE people made it for us and teach it us a lot of stuff. So we are using some of this knowledge today. But first, we will have to talk very briefly about what Kubernetes is and what it consists of, just so you have your understanding for the main part of the talk. To many, Kubernetes seems like an overly complex deployment tool, even unreasonably complex. The thing is that Kubernetes is not just a container orchestrator for running web application. It's useful to consider it as a whole operating system. Just as Windows, Linux, macOS, Android, and others abstract computer hardware from you, provide some unified APIs for programs to run, Kubernetes abstracts real servers from you, physical or virtual, and provides its own API. That's, in Kubernetes, you no longer care about how many servers you have and how many cores each one of them does have and gigabytes of RAM, and whether they break or reboot. And this API is declarative. You just tell Kubernetes, I need these containers to run and to be accessible on the ports on that domain. Do it. And it will do. So all you need is to package your application as a Docker container and then declare your application deployment in terms of that Kubernetes abstractions. While there are dozens of these abstractions in Kubernetes, an application developer only need to know about like 5-ish of them. So the first one is a pod. It's minimal unit of running application. Then replica set allows us to do horizontal scaling. Deployment is needed to do deployments, without downtime, roll and deploys. Service gives us basic traffic balancing and service discovery. Ingress allows external traffic to enter Kubernetes cluster and reach our application. And then Helm is a package manager, like apt, the tool that you use to package your app with its dependencies to be deployed. So for today's talk, we need to know only two of the squares, pod and service. Let's take a closer look. Pod, it's practically atomic unit that Kubernetes operates, a logically indivisible group of containers. In practice, as a rule, one container in the pod is the main one and others are auxiliary. They are also called sidecars, like motorcycle sidecars. For example, an application server instance running Puma or Falcon is the main container, and some log collectors, config watchers are sidecars. Containers of one pod always run together on one physical or virtual server and share the network between themselves. In fact, a pod should be considered as an independent server. It has its own IP address and host name. So, application server with Puma or Falcon or Unicorn is a pod. Background job processor with Sidekick or Solid Job is another pod. If you need to run more application servers, just replicate and run more application pods. And of course, a reminder that you should not pack all your application in one pod, so don't let run Puma and Sidekick together in one pod. It's an anti-pattern. Then we can skip a couple of components and look at services. Services logically group similar pods into a logical unit. give them an internal DNS name so other components of your app can discover them, and provides basic round-robin traffic balancing. Services allows application components to talk to each other without worrying of deployment details, scaling factors, and etc. Service is vital for horizontal scaling, and although scaling itself is performed by other components, replica set and deployment, the service allows us to not think about scaling and deployments and which pods are healthy, etc. So now probably we are ready to deep dive to nuances. Now when basics are covered, we can finally start the main part of my talk. And first in line we have automatic checks of our application health. As I already said, Kubernetes API is declarative, and one of the goals of the Kubernetes itself is to provide self-recovery for your application. For this, the platform must somehow understand when a component of your application has died or malfunctioned or overloaded to try to fix it. So there are three health probes exists. First one is, and most kind of important one, liveness probe. Is designed to detect that a container has stopped working, hung or freezed, in which case Kubernetes will shut it down and restart. Readiness check, on the other hand, is designed to determine that the container is ready to process user traffic. An unready pod is excluded from the service until it becomes ready. And third one is a startup probe, which was added pretty recently, a few years ago. It just allows to postpone both liveness and readiness checks, because both of them are being executed constantly, like every 10 seconds, Kubernetes will send a liveness probe and readiness probe to all your containers during all the pod runtime. So these checks should be very, very lightweighted. How are these checks configured in real life? People make some very lightweight route, like /health, that maybe even, not application controller, but, metal controller in Rails, very, very lightweight, specified as a health check that returns just, HTTP 200 OK. And then, without much hesitation, they copy and paste the same declaration to readiness probe 2. So two checks are used as the same endpoint, the same port, the same path, and it works. Well, most of the time. So there is a nuance. And this is request queues for processing inside each application server. Let's imagine a typical Ruby on Rails application. We have, for example, Puma with 2 workers. So when workers are free, they have capacity, everything works fine. But when all of them are busy, requests starts to accumulate in application request queue. And health checks also accumulates queue. So here comes high load. Your application become popular. Maybe some requests just start to take unusually long to process. Or maybe a user clicked several times to generate a long report. And that just so happens that all these requests hit the same pod. What happens then? Liveness requests also get to the same queue with other requests and does not get processed in time. Kubernetes decides that the container has hung and kills it. The container restarts immediately. The whole pod restarts immediately, but it takes some time to start, to load application. It may be a minute for big applications. Users see an error, quickly press F5, or maybe your front-end framework just retries immediately. More requests come to other pods, and their queues start to grow too. So more and more pods starting to become overloaded, and process repeats. The next pod gets overwhelmed and killed. The remaining ones get additional load and also overwhelmed, and it grows like an avalanche. In a few minutes later, your application is completely down. The worst part It's Kubernetes who killed it pod after pod by its own sharp scythe. The one who should have been keeping the app alive. What an irony. The solution to this problem is simple and counterintuitive at the same time. You need to run the liveness probe separately from readiness probe, from your user traffic, on a different port, or by executing not a request but some command inside a container to understand whether the application server is still alive. So in general, through the back door. In case of Puma, the simplest solution is to run a control server which has lightweight stats endpoint and is accessible without authentication. So running it without authentication is not very secure. So be sure that you trust other apps in your Kubernetes cluster and haven't accidentally exposed this port outside. Or you can write your own Puma plugin, for example, for this purpose that will just, respond, okay. Or you can pick as an example of Puma plugin from my gem for monitoring called Yabida Puma plugin, but I don't advise to use existing plugin for as a health check because collecting metrics is not lightweight. Don't do it. Just use it as an example. So, to summarize, liveness probe should be configured to check if the container is alive without interfering with user requests. While in contrast, readiness probe should use the same endpoint and be in the same queue as user requests. Of course, there's a danger that then liveness probe will stop detecting death on the main port, but then readiness probe will back it up. Just ask your DevOps to ensure that they configured monitoring for unready pods. While readiness checks are applicable only to web application, only to application servers, liveness checks are applicable to every component. So every pod should have its own liveness check. So for example, background job workers need to be tested for ability to process jobs and restarted if they fail. So for a sidekick, for example, you can use existing sidekick alive job. Yet for web application pods, failing readiness probe is the last thing that should happen. While it's hard to make a web application completely without slow endpoints, especially when third-party services are involved, but at least you can detect failures and slowness there and fail fast, displaying meaningful error to users before Kubernetes will put all your pods for cooldown. So use timeouts aggressively and add circuit breakers to your application. And to keep your application alive and ready, you should monitor that request queue wait time. It's an incredibly important metric for the application, much more important than, for example, CPU load, which does not really tell much about application health. So it's precisely the metric that shows how saturated with load your application is and whether you need to scale your application horizontally. If you have more than a few milliseconds of request queue wait time constantly, you should scale your application up. And if your requests in your queue never wait, it's always zero, then, well, you can scale down and save some money. So, and when you have a decent monitoring setup with all these metrics, Kubernetes actually can scale your application for you automatically. It can make scaling decisions both up and down looking at this metric. So monitor your application, scale it, and may the uptime be with you. Okay, we finish it with one nuance. Let's move on to the next. But before that, we will need to learn a bit more about Kubernetes. Yes, again, I'm sorry, it's complex stuff. Kubernetes abstracts from us the number and power of underlying servers. They're called nodes in Kubernetes speak. So we don't need to care how many servers we have and how powerful they are. We may have a few big ones or maybe hundreds of Raspberry Pis, But still, we need to somehow instruct Kubernetes to provide our application with sufficient resources for its work, and at the same time that some malicious or just buggy code won't consume all of them. To solve it, you can declare requests and limits for each container in a pod. Requests declare how much minimum resources the container needs to run. Limits declare how much maximum the container allowed to use. So as a resources, we have CPU cores and memory. So requests are instructions to the Kubernetes scheduler to reserve space on a node for this pod. That is, if our pod has requests of 200 milli-CPUs, then on a single core server, Kubernetes can place 5 such pods and no more. For example, in the figure above, there are already 3 such containers or pods, if we assume there's requests, that have occupied 0.6 CPU. And it doesn't matter how busy the processor actually is. It can be idle, or they might have all gone crazy and are mining cryptocurrencies. Kubernetes will assume that the node has 0.4 CPUs available for 2 more such pods, or for 1 pod with 400 milli-CPU requested. And Kubernetes will only look at declared container requests and node capacity, not actual consumption. Limits are complete opposite. They essentially configure Linux kernels on servers, on nodes. So, did you know that containerization in general is just a thin wrapper over Linux cgroups? So Kubernetes treats CPU and memory differently. CPU is a compressible resource from the point of view of Kubernetes. So if there's an overcommit and more containers trying to use it, then they will be throttled, but not killed. With memory limits, the reason is much more obvious. As soon as a container exceeds the limit, out-of-memory killer will come to it, and pod will be automatically restarted. One more nuance with requests and limits per se, without regarding to Ruby even, is about that they both are completely optional. You can deploy applications without specifying them, but did you know that behavior of your application is changed because of that, because of omission of requests and limits? And everything will work fine until there is not enough resources on a server, on a node, not enough memory, or, well, CPU is, 100% busy. In various combinations, requests and limits provide different levels of quality of service for containers. If you specify only limits without requests, or you specify both requests and limits equal to each other, you get guaranteed level of quality of service. It gives the best performance and reliability, but at the cost of underutilization of the cluster. You can save resources by overcommitting your cluster resources. If you specify only requests without limits, or specify both but they are not equal to each other, you get burstable level of quality of service. Burstable allows for more complete utilization of the cluster by overcommitting resources. If you don't specify both, omit them, you get the worst possible level, best effort. You are unlikely to want to use best effort for your application main components like application server or sidekick, because containers with it are killed first if there is not enough memory on the nodes they run on, and they get least priority for CPU usage and first to be throttled. So we learned a bit more basic stuff about Kubernetes, so now let's get to the next nuance. How Ruby performance affected in Kubernetes when CPU is limited. So on previous slide we have seen that we can limit our containers to use less than 1 core, but how it works. And we can be tempted to use fractional limits to save resources, as we know that single Ruby process can't utilize 1 core completely anyway, so why we need to allow to do so? So if we don't specify CPU limit or give a whole number of cores, the container will be allowed to use 100 of the core uninterrupted. But when we specify a fractional limit, Kubernetes instructs the operating system scheduler to allow processes of the container to be running only a fraction of time, some percent of 100 millisecond window by default. It's a C group setting. In this example with 400 milli CPU limit, container will be allowed to be executed on CPU only for 40 milliseconds for every 100 millisecond time span. So if a request needs 39 milliseconds to process, it will be completed in 39 milliseconds. But if it needs 42 milliseconds, it will be run for 40 milliseconds, interrupted for 60 milliseconds, and then run for last 2 milliseconds. So it will be completed in 102 milliseconds in total. That's unexpectedly slow. It actually can be fine for background jobs, you know. We don't care if they will be finished a bit later. But for pods, processing user requests is just not acceptable. So use whole number of cores as limits. You can request half of the core to schedule more pods on the same node, but use integer limits. And DevOps set up the CPU throttling high alert to catch pods that can't perform on their full potential. So we found out that we need to give containers whole processor cores to avoid slowdown due to throttling. Now we have a new problem. How to utilize this cores to the fullest and not overpay for idle resources. The nuance here is that Ruby and some other popular high-level languages like Python are actually not fully parallel due to global virtual machine lock in Ruby. And using only operating system threads, we cannot fully utilize single processor core by running single Ruby process. Also, in case of Ruby, one thread can execute Ruby code while others at this time can wait for response from database or network, process JSON with native extensions. So it would seem that it should be able to load process to 100% with a high number of threads, but now, in practice, it's difficult to see more than 50% utilization. The more threads you have, the more they wait for GVL, the less performance you get. The solution for this is actually old and well-known, but discouraged in the era of containerization. It's to use the clustered or hybrid multi-process and multi-threaded scheme, where the master process accepts requests from clients and distributes them to worker processes that it forks from itself. The container limits apply to this entire group of processes as whole at once, so we can get full processor utilization without throttling. And at the same time, memory is also saved due to the copy on write technique of the Linux kernel. As a bonus, worker process utilization also improves, since the master process knows which workers are currently busy and which are idle, and thus can distribute new requests more efficiently to exactly the free worker processes. In the case when we have one process per container and load balancing is done only by Kubernetes service, which is actually a simple set of IP tables rules under the hood, then the service simply distributes connection in round-robin fashion, just in turn to a next pod. And often there's a situation where some workers are idle without work, while others are completely busy and still accumulate requests in their request queues, and, you know, we are getting back to health checks problems. Thus, enlarging containers with web applications can increase throughput and reduce latency, not only due to increased processor utilization, but also due to more uniform of the application servers themselves, which reduces latency. And it actually performs better. Look at the recent benchmarks made by Nate Berkopec, where he compared many containers with single process multi-threaded Puma and one container with clustered Puma setup, and clustered Puma won, and difference is huge. And that's it for today. Thank you for your attention. Please find me in my socials, and let's chat about all things Ruby, Kubernetes, and Ruby on Kubernetes. And also, we have a lot of related and not so related blog posts about Ruby, DevOps, backend design, frontend, and everything else at Martian Chronicles, our company blog. Please check it out. And you can find the slides at this link. Thank you very much for your attention.
Thank you, Andrei. Any questions?
Did you see my presentation?
No, I
Oh, okay. That's okay. For the readiness probe, I used a log file, and the process writes into the log file when it's booted. And then for the liveness probe, I used Rails health check, like the /up. Is that appropriate? Basically, like the process boots, and when it's ready to receive requests, it will write into the log file, like, hey, I'm good.
It's a good thing for, the startup probe.
Yeah.
Yeah,
So is the readiness probe actually executed more than once? Is the readiness probe like executed multiple times?
yes, like by default, it's like every 10 seconds. Every 10 seconds, there will be a health check and readiness check in parallel.
What's the point of doing two probes?
So once containers stop to respond to that probe, affirmatively.
Yeah.
So if it doesn't respond to health probe, it will be just shut down and restart.
Okay.
If it doesn't respond to readiness probe, it will be excluded from request.
Also, a service can become not ready and then become ready again in the future.
Yeah, so it can, if it's got many, slow requests,
Yeah.
it can be excluded
From further request handling until it becomes available again.
yeah, processes them, finish it, and then can be brought up.
I see. Oh, that's very fascinating. Thank you.
A quick question. So I'm using Camel for my pet projects, and don't think that Kubernetes is the right thing for it. But what is the right time to consider it?
If you are happy with Camel, it's okay. It's a perfect one. Like for Kubernetes, when you grow up bigger and want, for example, to run your application for every pull request, like it can be better automated with Helm charts.
Oh, you mean sort of like review apps on Heroku, but self-hosted?
Yeah.
Is it cheaper than on Heroku?
Maybe cheaper, but often, clients come to us and tell us that we can't use Heroku, we want, a piece of it. And then Kubernetes gives you all flexibility. If you already, comfortable on some cloud provider, often there is not much value in migrating by itself. Unless you need, to add more microservices to the mix, like as I showed, like it's so easy, to add image proxy, any cable, a few radiuses, like one radius for, cache, one radius for stations, one radius for side key, and you can actually easily span all three in one Kubernetes namespace for every, for every pull request review app. That's flexibility that Kubernetes gives you.
Thank you.
Any other question? No? So we're going to have a 5 minutes break. Thank you.